AMATIC 2014 webinar series, An Alternative Approach to Presenting Gaussian Reduction of a Matrix with Steve DeLong. And this presentation is sponsored by the Mathematics Intensive College Mathematics Committee of AMATIC. And AMATIC is the American Mathematical Association of two-year colleges, and our core value is building expertise and exhibiting leadership in the teaching and learning of mathematics, enhancing personal growth and improving teaching methods and effectiveness as a personally initiated lifelong responsibility. And for more information, please visit our website at amatic.org. And please note that the views expressed by the presenter are not necessarily the views of AMATIC, and any commercial products mentioned by presenters are not endorsed by AMATIC. And now we're going to switch to Steve's slides here. So while I'm bringing these up, if you could all welcome Steve in the chat room, that would be great. And Steve has presented for us in the past, so I'm sure that you will enjoy his presentation. I see some rounds of applause as well, so let's turn over to Steve. Welcome, Steve.
Thanks a lot, John. Can everybody hear me okay? And thank you, everybody, for the greetings. I appreciate it. Okay, it looks like everybody can hear me, so that's good. My name is Steve DeLong. You probably saw that I also go by David DeLong. That's my first name, and because my father's name was David, my mother called me Steve, and that's really what I use for all my teaching and presentations, and that's just because that's the most common thing that I'm used to responding to. So, but if somebody were to call me David, that'd be fine as well. I've been teaching math for about 21 years now, and at the college level, and I teach both on campus and online. And I've always enjoyed teaching undergraduates, especially at the levels where they're at the junior or the freshman and sophomore level. Also taught through the senior level, and one graduate class I taught over the course of my career. But I don't have a PhD, so I'm not at a university, and I really just like to talk to people about math. The concept that is going to be discussed today is, of course, about Gaussian elimination. You can use this to find the inverse of a matrix, or you can use it to solve a system of linear equations if you so desired. It's one of the very many methods of solving systems of linear equations, and students tend to hate this one. I'm not quite sure why. They don't like to go to matrices, even though it's sort of nice to use computer methods if you convert to matrix methods to try and solve systems. And so I would have thought that students would have enjoyed it a lot, but they tend not to. And there are various reasons that we'll discuss about that in a moment. The presentation that I'm going to give you today is actually one that I discussed several years ago, and I was talking to a colleague of mine named John Gallo on campus one day, and he was talking to me about an idea about a presentation for that he wanted to give at a conference, and he was thinking about how he would prepare his application to present. And when he described it, I had to break to him the bad news. Well, John, I actually talked about this several years ago, and he was kind of stunned, and he said that he had never seen it before, and that he really thought that it was an interesting idea that should be discussed. And so he encouraged me to apply to present again on it. And so I thought that it would be fun to do, because I think that a lot of people don't give too many thoughts to alternative methods of presenting concepts, especially young instructors. I think I remember when I was a beginning instructor, it would be very rare for me to veer off from what the author was doing in the book. I felt like the author knew better than me, and I would say 99% of the case I would agree with that even today. I trust their expertise, but I've also come to believe that there are other ways that you can present ideas to students that don't interfere with the means that the author has used, and that also gives students a chance to get a concept accurate much more regularly. And so I wanted to go ahead and just try this, and actually it violates a precept that was taught to me when I was an undergraduate, when I was a senior, and I was just thinking about going into teaching, and I was talking to my advisor, whose name was John Beachy at Northern Illinois University, a wonderful instructor who's forgotten more math than I'll ever know. And he said to me one thing, the one piece of advice that he would give me, which was at the very end of my time at Northern Illinois, was I asked him, well, as I get ready to start to teach, do you have any advice? And his advice to me was one that I had violated when I first tried this technique, and that was to never compose at the blackboard. In other words, don't ever start to make up problems at the blackboard. Everything mapped out for yourself before you go into the class. Even if you haven't worked out the examples completely all the way through, at least have them set up ahead of time and work them out ahead of time so that you know if you're going to run into any problems. And in this case that's coming up, I actually did decide to compose at the blackboard. And fortunately, it worked out well, and the students actually had a surprising reaction to it, which was very positive. I don't recommend even now composing at the blackboard, but still, we'll get into that as we go along. So let me get started, and we'll just introduce the problem. I'm sure that all of you are aware of what the problem is, but I think that we'll go ahead and we'll just discuss it here. So now, John has told me that my presentation isn't in slide form, it's in a PDF form, so we're going to try and scroll and see how this goes. I'm going to go to the next page and see if it works for me. It did. Look at that. Okay, great. The traditional method to using Gaussian elimination to find the inverse of a matrix. Okay, now I think that we all know how this basically works. You're going to take your matrix, which will be square, and it will be non-singular. So we already know that there's an inverse to it. So the student has already determined that there is an inverse, or we've told them for argument's sake. You're going to adjoin an identity matrix to your given matrix A, and then you're going to use elementary row operations, obtaining a leading one in each row of the new matrix, then continuing row operations to transform the left half of the matrix into the identity matrix. When you're finished, the right half of the matrix is the inverse of A. And I think that that's a fairly well-known algorithm. Students tend to understand it, at least in theory, fairly well. Is everybody aware of what I'm talking about here? When I mentioned that this is a fairly well-written, well-understood algorithm, do you all know what I'm talking about if we were trying to find the inverse of a matrix? Okay. I was hoping so. Usually when I talk about this sort of thing to people, I assume that it's well known because we're all instructors. And we've all done this probably a million times more than we wanted to in life. But oh, they certainly do love to do it on the test, Ralph. I would say that my students hate it when they have to do it on a test. But the trouble with this method is that in all but the most convenient cases, the process leads to matrix entries that are difficult for students to handle. And what I'm thinking about is there are cases that you can use that give students nice whole number values in all of their matrix entries. And students tend to handle that fairly well, but that's not a very realistic situation, and it also doesn't challenge them very much. And as soon as you throw fractions into the mix, all of a sudden your life decidedly goes downhill, or their life goes downhill. And many students will, I remember that when I was doing it in class and I had a problem that had fractions in it, the students really got a little bit upset in one class. And this is what sort of led to this concept that I want to talk to you about today. Because one of the students in particular raised her hand and said, isn't there another way that we can do this, that we don't have to run into fractions? And I had never really thought about it before, but I just on the fly kind of said, well, yeah, there are ways that we can avoid fractions here. It might involve some large numbers by the time that we're done, but we could push it and avoid fractions. And she said, well, how? Can you show us? And that was when I decided to go off the tracks and veer from what my advisor had told me and go ahead and compose at the blackboard. And so I decided to make it up as I went along. Now, the first example that we're going to do here today is going to deliberately be nice. So it could be done by the traditional method without any difficulty at all, and most students would handle it, I think, fairly well. But the second example will illustrate to you how you could allow yourself to work with a really complicated example, and the method would still work very nicely, and students have a high degree of success. So let me show you what a typical problem would be. Find the inverse of the following matrix. And the determinant of this matrix is pretty obviously -1 if you calculate it. 4 times 8 is 32. 11 times 3 is 33, so 32 minus 33 is -1. Lost, oh, I shouldn't use that pointer, I guess, because it's wiping out some of my writing on the old screen. But the determinant is -1, so this is invertible. So I don't know if you can see it, but it looked like when I moved that hand across the screen that it wiped out some of the writing on there. But it's supposed to be -1, so the determinant is -1. Oh, okay, then it's just me. Okay, great. Thank you, Saracen. I appreciate it. So it must just be when I move this little hand icon around. Okay. Now, if you think about it, okay, well, I'm not using the pointer. I just was moving the mouse around the screen, Saracen. So that was my problem here. So maybe if I use the pointer, it would actually stop that. Oh, there's the pointer. I don't want to use the pointer. Sorry. Okay. All right. So let's see. If you think about this particular problem, I think that we could all, as instructors, we could see a technique where we could work this out if we wanted to use the traditional method. And let's remind ourselves about how the setup will go. So if I was to set this up to try and calculate the inverse, it would start out like this. I would adjoin the identity matrix on the right, and then I would try and transform the left half of this to an identity matrix. Now, what you could do if you were going to try this one is that you could multiply the top row of the matrix by 3, and then add -1 times the second row to the first row, and that would give you a leading 1. That requires a certain amount of insight that many students don't really see when they're first doing a problem like this. And their alternative is that they could divide the first row by 4, and you could see that that would lead to calamity right away, because you would have 1, then 3/4, then 1/4, and 0, and suddenly they would have fractions every place. Even worse, you could divide the second row by 11, and that would give you 1, 8 over 11, 0, and 1 over 11. And that would be enough to send just about every student in the classroom shrieking into the hallway, looking for higher ground, I suppose. Okay. Now, the alternative approach to this, which is what I brought up in class on the day that I was describing this, was, well, we could instead just decide that we wanted to only work with whole numbers. And it seemed to me like it should work at the time. And what I thought after I started down this path was, maybe I should have mapped this out ahead of time, but it was too late. I had told this girl in a very confident tone of voice, yeah, there's this alternative that we could use to avoid fractions and just use whole numbers. And now I was committed, so I had to actually go ahead and do this. So what I decided to do, or what I told her we should do, is multiply the rows by constants to make the first column entries identical, with the top entry being positive and the lower entries being negative. And so you could see that I chose the least common multiple of the two values. So I had 4 and 11, so the common multiple is 44. So I multiplied the top row by 11. That's where I'm getting the 44, the 33, the 11, and the 0. And I multiply the bottom row by -4, which gives me -44, -32, 0, and -4. And you can see that everything is getting larger, but it's all whole numbers. Okay, does everybody see what I'm talking about here for this particular step? What I'm doing is just trying to unify the first column entries. Okay, and I'm sort of ignoring the fact that the numbers are getting larger, but everything is nice and whole number valued, well, integer valued, I suppose we should say. Exactly, Ralph. It's an elimination method, and it's kind of a nice process. The students all seem to be accepting it very well. The next step is just to add the first row to the lower rows, and you notice what's happening here is that now I've got the 0 in the 2, 1 entry, which is what I was trying to reach. I'm trying to get the left half of the matrix to be the identity matrix, and everything is working fine. I've got integers every place. There's no fractions. The students were all still very calm, and I asked them all, well, does everything make sense to you, what we're doing here? They were like, yeah, okay. And now I said, well, now let's do the same thing to the second column. Let's try and make the second column entries to be the same, okay, except one of them should be positive and the other one should be negative. And I said, well, what's the least common multiple of 1 and 33? And just about everybody immediately snapped out, well, it's 33. So I said, well, let's multiply the the second row by 33 and the first row by -1. So we're doing basically the same thing. Now I looked at them all and I said, now you notice that we're getting larger and larger numbers, but don't worry about it. We'll take care of that all in a minute and it'll all smooth itself out. To be honest with you, when I was doing this, I was starting to panic a little bit because the numbers were growing even larger than I had anticipated. But everything seemed to be fine. And so I was rolling along with this presentation. And now what would you do is that you would add the second row to the first row, okay? And that should get you to very close to this, the identity matrix on the left. So add the second row to the upper rows and you get this, okay? Now, all the steps here, you notice I'm just multiplying rows by constants and adding rows, one row to the other, okay? And the students were all doing this fairly well. And I said, now, look, we are very close to the identity matrix on the left half, and there's only one thing that we have to do at this point, and what would that be? Okay, and so I asked anybody in the class to volunteer what we should do next. And the response was almost immediate. Most people just jumped out with it. But I'll ask you, what do you think we have to do next in order to get to the identity matrix on the left half of the matrix? Divide the top by -44. Absolutely, Dan. And divide the bottom by by 33. Exactly. For some reason, I thought it said 133. And students just cracked that out. There was no problem at all. They just immediately snapped it out. And I said, all right, well, let's do that. Okay. And we had it. Okay. All of a sudden, we had this this nice result where all of the left-hand side of the matrix was the identity matrix. And the right-hand side, of course, is now the inverse of the matrix. Okay. Everybody see what I'm talking about here? So we basically reached where we would have reached with the traditional approach, and the right half is the inverse of our matrix. Okay, so the right half of the matrix is the inverse that we want. Anybody with a question so far? I see a no, so that's good. A no. Thanks, Caleb. You know, that's one way to do it, John. That that some people just say, well, we always should be multiplying, and that's fine. I always do it by division because, like I said, since I've started to deviate from what authors will do sometimes, now that I'm writing my own books, I kind of sometimes do things the way that I think could be that the students accept more readily, and they seem to like to divide more than they like to multiply by fractions. You know, Ralph, that's going to be my next problem that I want to show you, because the next problem that I want to give you is a problem that I put onto the test. And I wanted to illustrate to you how, even though numbers get to be huge, it doesn't bother the students. Once they tried this method, the reaction that I got from this is that students said, well, that's easy. Why don't we just do that all the time? Why doesn't the author do it that way? And I said, well, it's just an equivalent way of doing it, and the author is doing it by the traditional method. That's the way I was taught, and it always works, and it just requires a little bit of insight. And they didn't like the fact that the author was often shuffling rows and things like that, and moving the matrix around. And in this approach, you never have to actually move any rows around. You never have to interchange the rows of the matrix. And so, you know, after I did a problem that was just like this, and I remember that I set it up on my first one so that I had a nice matrix with determinant 1 in this case. But when I was at the board, I said to students, well, you know, you have to realize that things could get a little bit hairy if we don't have a really, really nice matrix. The numbers could get large. And they said, well, we can, it doesn't seem to be like it'd be hard. It'd just take a little bit of time maybe to reduce fractions. So I did a larger problem on the board, and I wanted to share with you guys the problem that I put on the test. Because on the test, I told them, look, this method could get to have large numbers, and they actually challenged me, and they said, well, as long as they're not over 1,000, it should be fine. And I was like, okay, well, let's find out. So I decided to do a problem on the test that had this 3 by 3 matrix. Now, what I did say on the test was that this was invertible. Okay, so I lifted from them the requirement that they demonstrate that this was invertible. And I said, find the inverse of this matrix. And you can see that if you were to try it with the traditional method, if it was one of us, I think that we would probably all say, huh, you could take -2 times the third row and add it to the first row, and that would give you a leading 1, and then you'd be off to the races. But most students wouldn't see that. At least none of my students do. Maybe your students are better than mine, and they would recognize that. But that's my students do not recognize those sorts of things. So let me show you how this worked. And this was an actual test problem. And I want to show you how large the numbers got. And then I want to show you what the success rates that I was seeing from students were. Because one of the things that I've decided over the years is that if it's not something that I can demonstrate that the students are actually succeeding in, then I think it's kind of pointless. I may think it's easy. I may think that it's straightforward. But I like to keep records, and I like to see how the students are doing on things on the test and compare them to other methods. And if I can demonstrate that students are doing better, then now I'm on to something. Okay. Now, once again, the first step agrees with the traditional method. We take our matrix and we adjoin the identity matrix on the right. Now, in this case, obviously, it's 3 by 3. The students clearly knew that they were in for it on this problem, because whenever you get to something that is larger, 3 by 3 or 4 by 4, God forbid for them, then you know that you're in for some computations. Okay. Once again, I said let's unify the first column entries. Now you notice here that because I've got 5, 7, and 2, their common multiple is surprisingly large. It's 70. Okay, and I thought that this was going to make a lot of the students go nuts, but they didn't. They actually did fine on this. They said, all right, well, 70, we need 70. And on the test, I think everybody got the first stages of this absolutely correct. Now, some people went off the rails later on, as you'll see when I give you the data for how well they did on this problem on the test. But you can see that I multiplied the first row, I suppose, by 14 to get 70 in the first entry. And then I multiplied the second row by -10 and the third row by -35. Now, clearly the numbers are growing in size. Okay, and once again, as I say, the students did not panic about this. They just sort of went on, and nobody was griping with me about it. 0 in the 2-1 and the 3-1 entries. The numbers are growing, okay, and that's something that I warned them about, that could happen. Now, one thing that you could do, and the students liked this when I presented this as a in class. When I worked on this in class and I handed out some notes to them, I did suggest that there was something that they could do that would, if they felt like it, which was optional, you can actually control the growth of the numbers in a fairly natural way. Can anybody give me an idea about how you could shrink the numbers down after you did this sort of step before moving on? It's a fairly obvious thing. You could divide, Caleb says, by 7. That's one thing that you could do. Susan says multiply the row 2 by -1/2. Ralph, I would have said that too. Divide the second row by 2. One of the things that you're all on the trail, you're hot on the trail of what I'm thinking about. What I said was find the greatest common factor in each row and divide by it. So you could shrink the numbers back down, and you're all on that trail. You're all thinking the same way that I'm thinking here. You could start out by dividing by any common factor that you see, or you could go for the greatest common factor. And we had just covered greatest common factors not too long before this in another problem. And so the students were kind of eager to demonstrate that they could do that. So what I did was I said, let's divide all the rows by the greatest common factor. And you notice that that's what happens here, is that I divide every row by the greatest common factor. And you notice that the numbers all shrink back down again. And the first row actually goes back to where it was originally, because it was a fairly easy step to see that. because we had multiplied the first row by 14. So it was just divide the first row by 14 again, and you could get back down to some reasonable numbers. Okay, so you all see what I'm talking about? So you could just divide by the greatest common factor in each row, and that gets you back down to some nice numbers. And the students seemed to like that. It was just perfectly fine for them. Okay. Look at see what my next slide is supposed to be here. Okay. Now I think that you can all kind of get the idea about what's going on here. Now the next thing that you would do is that you would approach the second column the exact same way. Okay, so you would figure out what a common multiple of all of those numbers was, 7, 22, and -1, and you would get them all to be the exact same number. Now in this case, 7, 22, and -1, their common factor or common multiple, I suppose, would be 154. So it would be a large number, but as I say, the students didn't seem to object to it too much. And so they did it just fine. I'm going to relieve you from having to watch me do all those steps, though. If you continue on through all of the steps and you go to actually get to the form where you're close to the identity matrix, which is exactly the same set of steps that we did on the first smaller example, you wind up getting to this point that's right here. I've got 924, -154, and 252 on the main diagonal on the left. And the numbers got large, as you can see, but the students did surprisingly well. As a matter of fact, I believe that when I did this, it was almost 90% of the students got to this point without any trouble. The next thing that happened was going to be a little bit of difficulty for them because you know what's coming next. You have to divide both sides of this, every row by 924, -154, and 252. And that was where they ran into fractions. And if anybody lost points, it seemed to be that it was there. Because now we're talking about a little bit of reduction, but it was mainly nice. Most students handled it very well, and they had a lot of scratch work off to the side. I will say that. When they wound up having to reduce the fractions, there was quite a lot of scratch work going on because the numbers are fairly large at this point. But most people got it actually correct when they finally did it. Dividing by the 924 in the first row, the -154 in the second row, and the 252 in the third row, you get all of these fractions. And now you've got your inverse on the right-hand side. And students did extremely well. I was very surprised and pleased at how well they did at finding the inverse. And doing this particular one by the traditional method, I will tell you, is a dumpster fire. So if you try and do it by the traditional method, you wind up with some rather horrific values. And students tend to really struggle with it. Okay. I think the method for us, for instructors, is fairly straightforward. Okay, I'm going to make that as a guess. Would you all agree that the technique from an instructor's point of view is actually fairly straightforward? I mean, the method seems to be fairly easy to follow. The steps are kind of nice. You don't see it in any textbooks. I'm kind of curious why you don't see it in textbooks. Ever since I made it up that day, it just seemed like it was a natural to do in class. Amber, I would really recommend it because you'll be surprised, especially if you show students the traditional method, you'll be surprised at how much they prefer this. It seems, it is a little bit less efficient, Saracen. What I said to the students was that there's a price to be paid to avoid fractions. Now that price is going to be that we're going to be a little bit less elegant. We're going to have to go through a few more steps. Oh, okay, sir. Steve, sorry. Well, I can remember that because I'm Steve too. And they didn't seem to worry about it. They said, well, if we can avoid fractions till the very end, that's worth it to me. And so I thought, well, okay, if you don't mind having a couple extra steps, that's, okay with me, as long as you get the matrix inverse. That's what I was interested in. And of course, you could obviously do this to solve systems as well. I mean, there's no reason that this would be restricted to solving, to finding the inverse of a matrix. You could use this to find the solution to a system of linear equations just as well. It would even be easier than finding the inverse of a matrix because you wouldn't have quite as large a matrix to do. What I did then was that I compiled some information because, as I said, I like to, for some reason at the time, I think I was heavily into assessment on our campus, which is, let's see, Ralph says, it's important to me that linear algebra students are comfortable with fractions. It should be. Yeah, Ralph, they should be. And, you know, when you get to linear algebra, you probably should insist that they do it. I was thinking mainly about college algebra and calculus when I was interested in having them see some of this stuff. But if we were getting to linear algebra, you are absolutely correct. There are some things that when we get to the upper levels of classes that even if they are tedious, the students should be able to master them and they should be able to handle them with a certain amount of dexterity. And I agree with that completely. And when I'm at those upper levels like differential equations, calculus 3, linear algebra, things like that, then I tell them that this is something that you should be able to do. So fractions are not something that you should be avoiding. So you're absolutely correct, Ralph. So 100% with you on that one. So thanks for pointing that out. I see Ralph still typing, so that's what I'm waiting for. Or maybe Ralph just is moving his mouse. Hard to tell. It is nice, Ralph, and I especially like it for people who are not intending on going into math as a major, and they really, you know, they need to know how to manipulate numbers fairly well. And this one is one of those things that I think that they like it as an alternative. So let me show you what my outcomes were. Now, I was teaching some fairly small classes at the time, but this is what I came up with, okay, with my traditional method. I probably should have put the titles of the tables above them rather than below them. The top one is when I was doing the traditional method, and what I'm talking about here are examples that did not involve like really, really nice whole numbers. Whenever they involved fractions, how were the students doing in terms of success on this problem when you had fractions involved in your matrices? And in my classes in college algebra, pre-calculus, calculus, and linear algebra, I was actually having a fairly low success rate. Now, the linear algebra class you can see was pretty small, okay? Yes, they are, John, but students told me in class that they weren't running into problems that didn't have fractions in their homework, and they were irritated that I was taking the easy way out and not doing fractions in class. And they felt that that was unfair to them. And so they let me know that in a rather loud voice. But you can see that the success rates for students when they involve fractions were fairly low in the traditional method, and then they soared when I did this with this alternative process. Students were doing remarkably well. In calculus, of course, they were doing extremely well. It was a fairly low class size, okay, that I was working with, but you can see that the success rates really jumped. In college algebra in particular, they increased by 400%. In pre-calculus, they more than doubled, and in calculus, they almost doubled. So students were doing extremely well in these classes and in this problem set. And it didn't matter how complicated the questions were. They were getting here. Let's see, Ralph, for the traditional one, I think that it was for college algebra, there were 7 classes. Pre-calculus, it was 6. Calculus, it was 4. Linear algebra was 2. And for the advanced one, for the alternative method, rather, there were 7 college algebra, 4 pre-calculus, and 4 calculus. Okay. Well, Sean, I was lucky. Okay, so I had that. Yeah, so I had fairly small classes. But these were taken over several years, so I did this over a series of semesters here. So yeah, I don't envy you for having 33 in a linear algebra class. That would be really difficult to manage. However, I do notice here, or I noticed, and I would be encouraged. I would be very curious to see what other people found, what your success rates were, because as you can see here, the success rates for students were extremely high for this alternative method, and they were rather low for the traditional method. And this is when I was involving fractions. So I specifically was looking at problems that did involve fractions, and I noticed that in the traditional method, students were having all kinds of problems with trying to move rows around. add multiples of one row to another when there were fractions involved. It just seemed like they were going off the rails, and that wasn't the point of the problem, and that was really what was distressing me, and that was why I went to this alternative method. You notice that I had never tried the alternative method in a linear algebra class, so much like what Ralph was saying before, in linear algebra I figured, you guys should be able to handle the traditional method. So linear algebra never was presented with this alternative because I wanted them to be able to actually do the manipulations that they were supposed to, because there are other reasons that you want to do this process in linear algebra, and you want them to have facility with working with matrices. So Ralph, I hope that you agree with me on this one, that it was not wise to do it, or not desirable to do it in linear algebra, so I never did attempt that. But I imagine that linear algebra students would hit it out of the park if you had them do it. They wouldn't be objecting to it at all. But when we got to that level, I thought, wow, you guys should be able to handle it, so I didn't bother to modify my approach. Okay, so anybody with any questions? I think that what I'm hoping that you take away from this conversation is A, that there's an alternative to Gauss-Jordan elimination, and B, that students really do well in it. So if you're having trouble with students, in particular, as I say, at the college algebra, pre-calculus, and even calculus level, and you want them to just find an inverse matrix, it offers you an alternative, not necessarily a better alternative. I think it's better. Students liked it a lot more. I got a lot less blowback from students when they were facing matrix problems because they didn't care about fractions. They seemed to worry about it a lot less. The general comments that I got from students was that this was easy, and that was something that I was really pleased to hear from students. They were very successful with it, and they asked me why it wasn't done in the book this way. So I think that they got a lot out of it. I thought that I was pleased by their results, and I was very pleased by the success rates. And as I said, I don't pretend that this is rocket science. It's, I think that you're right, Ralph. If you give students an option on solving systems, they'll jump to elimination just about all the time. And this is very close to elimination, so you're right. Yeah, Cynthia, I've talked to some other people when I presented that said that they had done this as well. Never appears in a book. I'm very curious about that. I'm writing a book now on math for nursing, so we don't cover this topic, but I haven't seen it in any books, so I'm very curious why not. But it's just one of those things. It's probably just the traditional approach that just is dominant, and we all teach, I suppose, what we learned as students. No kidding. So in a finite math book. Cool. Excellent. All right. Okay, so that was the technique that I had. That was what I wanted to discuss with you, and that could be, Ralph. Yeah. So this would be easy to program as well, though, I would think. Oh, Teresa, it's in the works. So we're working on a version of my math lab to go with it. So I'm very excited about it. So it's my second textbook, and so I'm quite excited about it. But that's down the road, so watch for it. So I will. Hopefully, you'll see my name as a possibility for a book adoption soon. So we'll see. Okay, John, I think that I've reached the end of my discussion. Did anybody with any questions about anything before I turn it back over to John? I hope you have a lot of success with it, Caleb. I found that, like I said, students did really, really well.
Well, if you all want to thank Steve again in the chat room, that would be great. I'm sure that Steve will take a few more questions as well. We have a little bit of time for that. But Thanks again for participating in today's AMATIC webinar, and if you'd like to support future AMATIC webinars, please consider becoming a member of AMATIC at bit.ly/join-amatic. And please remember to like us on Facebook at facebook.com/amatic. And recording of past AMATIC webinars can be found at bit.ly/amatic-webinars, and it typically takes us 1 to 2 weeks to produce and upload webinars to this archive. And please take 2 minutes to evaluate the webinar content and the presenter at bit.ly/amatic25. And if you need email confirmation of your participation in this webinar, please fill in the optional section at the end of the evaluation. So I'm going to end the recording now, but I'm sure that Steve will stick around for a few more questions.